Warning, the 50,000-degree wall protecting our solar system. The counters jumped before anyone spoke. Energetic particles fell off a cliff, cosmic rays surged, and a thin hiss in Voyager 1's headphones rose like a siren. "Something out there is hotter than any star's breath we expected here," I said, staring at a spike that shouldn't be possible so far from any sun. A 50,000-degree wall, too hot to make sense, too thin to burn metal, pressed against the edge of our solar wind. If it protects us, what's it keeping out? What is this boundary? How does it shield life? Where does it leak? And who holds the thermostat? Us, the sun, or the galaxy? The threshold, when the counters spiked. Voyager 1 was running on borrowed time. Power was rationed like air in a damaged sub. Heaters starved, instruments rotated, every watt argued over. Everyone knew there was one more crossing left in the old machine. Get it wrong, and we'd misread our own front door. The first hints came as nuisances, numbers that didn't settle. The charged particles we'd tracked for decades began behaving like nervous animals. Sudden drops in solar-borne ions, stepwise rises in the most penetrating cosmic rays. Then the magnetic field nudged right, then left, rotating in a way that made the room go quiet. That field line was supposed to be our map. Instead, it was a riddle. On a Tuesday that felt like a held breath, a solar storm launched months earlier finally reached the outskirts. Voyager's plasma wave instrument, two long antennas wired to hear the universe, picked up a tone. It wasn't music, but it had pitch. The frequency crept higher, a sure sign the electrons out there were packed closer than in the heliosheath we knew. That hum was the giveaway. The medium had changed. We were pressing on something denser. Meanwhile, far from the frontier, a small spacecraft orbiting Earth had been painting the sky with a new kind of light. IBEX turned invisible atoms into a globe-spanning image, revealing a bright ribbon arcing across the sky, an energetic neutral atom signal no one predicted. Cassini, orbiting Saturn, saw hints of the same thing with Inca. From two vantage points, the maps whispered the same sentence: there's structure out there. Inside the Voyager team, the debate wasn't polite. One camp saw the cosmic ray jump and said, "Outside." Another pointed at the magnetic field's orientation, which stubbornly refused to flip as cleanly as models expected, and said, "Not yet." The wall wasn't an official term, but it crept into hallway talk because nothing else fit how abrupt it felt. Here's the human side. An engineer who'd kept the spacecraft alive through 3 solar cycles rubbed his eyes and muttered, "If this is the end, it's a good end." A plasma physicist leaned over a printout and tapped the rising tone with a pen. "Listen to the density," she said. "The electrons are telling you where you are." In that moment, the sound mattered more than the picture. Stakes weren't abstract. If we mislabel the line, we misunderstand the shield that shapes every dose meter on the ISS, every silicon error in a satellite, every plan to send humans into deep space. The counters weren't just counts. They were the heartbeat of the bubble that made our planet habitable. The anomalies stacked. Solar particles born inside the heliosphere dropped to near zero. Galactic cosmic rays, once pushed back by the sun's breath, flowed in, not like a flood but like a tide no longer resisted. The magnetic field strengthened and steadied, but its direction didn't spin dramatically. That single fact kept the arguments alive. Was the heliopause a clean border or a set of laminated sheets, tangled by reconnection and draped in the interstellar field? While that was happening at the edge, IBEX's ribbon refused to behave. It brightened and dimmed with the solar cycle, as if responding to the sun's mood swings with a half-year delay. The ribbon's geometry pointed to a magnetic field outside, draped around our bubble like a taut fabric. Cassini's images supported it. Voyager's touch gave it weight. 3 very different instruments, one uneasy conclusion. The frontier wasn't empty. It was layered, structured, alive. Then came the day the plasma wave tone leapt. The pitch mapped to an electron density tens of times higher than the heliosheath's values. If you've never seen a room full of scientists listen, really listen to a graph, it looks like superstition. It is. The frequency is physics. Higher frequency meant more electrons. More electrons meant we'd pressed through to the very local interstellar medium. Not a guess, a measurement. But there was one problem, and it mattered. The temperature inferred from various models of that outside gas said hot, tens of thousands of degrees. Everything we were trained to feel about hot screamed danger. And yet Voyager showed no signs of roasting, because in space, hot can mean very few particles moving very fast. Heat needs collisions. Out there, collisions are rare. The sensation of a furnace with no burn would haunt the rest of the story. In the aftermath, the word outside landed in headlines and phones rang. Inside, the conclusion was sharper and stranger. We'd breached a barrier that filtered radiation and sculpted a sky map from Earth. But the barrier wasn't a wall like a brick, more like a bruise, a region where two forces met and left a mark. The term stuck because bruises have edges you can press and feel, and that's what the instruments were doing, pressing. One detail buried in that first density spike would matter later. The exact pitch of the plasma wave, the way it climbed, told us not only that we were in denser stuff, but by how much. That number, electron density, would become our yardstick for every later storm, every echo, every map we drew of the boundary's thickness. The wall had a voice, and we'd finally learned how to hear it. To understand why the edge burns without burning us, we have to go back to the sun's breath. The sun's breath builds a bubble. To understand the bruise, start with the breath. The sun doesn't just shine, it blows. From every latitude, charged particles stream outward at hundreds of kilometers per second, dragging the sun's magnetic field with them. That outflow is the solar wind, and for most of the journey it's supersonic, faster than pressure waves can travel in the plasma. It races past Earth, past Jupiter's storms, and keeps going until it can't. Where it can't is called the termination shock. Think of a freeway that slams into a traffic jam. Upstream, cars fly. Downstream, they crawl and heat. The solar wind crosses that invisible shock and drops from supersonic to subsonic, turning kinetic energy into internal energy. Downstream of that, in the heliosphere, the wind is hot and turbulent, redirected tailward, trying to find a way around the competing pressure of the galaxy beyond. Every swirl, every eddy, is the sun negotiating with the interstellar medium. What nobody knew at the time Voyager launched was how alive that negotiation would be. Pressure isn't just one thing. There's thermal pressure from hot ions, ram pressure from the wind's bulk motion, and magnetic pressure from frozen-in fields. On the other side, the very local interstellar medium pushes back with its own particle pressure and a magnetic field that drapes around our bubble. Where those pressures balance, you get a contact discontinuity, the heliopause. It isn't a wall you can touch. It's a boundary that exists because forces agree to disagree there. Meanwhile, something else was happening that made the edge stranger. Neutral hydrogen from interstellar space slips across the heliopause because it's, well, neutral, uncharged, and blind to magnetic fields. Inside the heliosphere, those neutrals swap electrons with hot ions in a process called charge exchange. You get energetic neutral atoms that fly off in straight lines and cold ions that can be picked up by the solar wind. Energy moves. Momentum moves. The boundary starts to glow in ENAs you can image from Earth orbit, which is exactly what IBEX did when it revealed that ribbon arcing across the sky. Here's where it gets personal. The first time I saw a simulation show the heliosphere inflating and deflating with the solar cycle, it looked like a heartbeat. During solar maximum, when the sun's magnetic field is tangled and eruptions are common, the wind's average pressure rises. The bubble swells, the heliosphere thickens, and the boundary is pushed outward. During solar minimum, the wind softens, the sheath thins, and the edge drifts inward. Not much by our standards, tens of astronomical units over years. But for a spacecraft like Voyager, that's the difference between silence and song. But there was one problem. Space outside isn't uniform. The interstellar medium looks smooth on a map, yet it's a patchwork of partially ionized clouds, ripples in magnetic tension, and density gradients that have their own histories. We're cruising through the local interstellar cloud, skirting structures tied to the local ribbon of cold clouds. As the sun moves, the interstellar field lines don't just sit there. They drape and twist, creating places where magnetic reconnection can bleed energy, where folds can create doorways, and where the solar wind's deflated croissant shape, or comet-like tail, depending on who you ask, decides how stresses distribute. While that was happening out there, back near the sun, the 11-year cycle quietly set the metronome. Flip the sun's magnetic polarity, and you change how its field threads the wind. That threading determines how cosmic rays are modulated as they try to work inward. It also sets the stage for how shocks from coronal mass ejections will pile into the heliosphere and ring the heliopause like a bell. Those are the very shocks whose echoes Voyager's plasma wave antennas would later turn into that rising tone. The heartbeat isn't just a metaphor, it's causality you can measure. So what shapes the bubble? Start with ram pressure, density times velocity squared of the solar wind. Let it crash into the total pressure of the VLISM, thermal, magnetic, and a trickle of cosmic rays. Add charge exchange, which siphons energy and seeds a population of pickup ions that act like a ballast. Stir in turbulence that cascades energy from big flows to small eddies, where it becomes heat. Then overlay the draped interstellar magnetic field, which adds tension like elastic bands around the bubble. Where this stew reaches stalemate, the heliopause forms. Get this? The balance isn't static and it's not symmetric. The sun's rotational equator is tilted relative to the galactic magnetic field. North and south lobes feel different stresses. Tail regions stretch or deflate depending on how tensions resolve. That's why the debate over comet tail versus croissant lobes isn't just an academic food fight. It's about where the bubble is strong and where it's thin. If you're plotting a human mission out of the ecliptic, this geometry isn't wallpaper, it's risk. Now remember that bruise metaphor. A bruise forms where pressure meets tissue and blood pools. Our boundary forms where pressure meets pressure and energy pools, some of it ending up as 50,000 K temperature that won't fry a hull because particle densities are too low to share that heat. That's the paradox we ran into at the end of the last act. The bubble's very existence makes that paradox inevitable. Accelerate a few particles a lot, and you can call it hot without ever feeling warmth. And yet this bubble is why life on Earth evolved under a certain radiation budget. Without it, the most damaging galactic cosmic rays would reach the inner system far more easily. With it, the sun's breath sets the baseline, thickening and thinning the shield over decades, shaping mutation rates subtly over eons. The bubble is our home's first line. It breathes with a star, flexes against a galaxy, and leaves a mark we can press with instruments and hear as song. Which raises the next question. If the edge is hot with almost no heat, where does that heat really come from? Where heat comes from when there's no fire. We called it hot, but not the kind of hot your skin understands. Temperature out there is a measure of how fast particles move, not how warm something feels. In a kitchen, heat leaps by collisions, billions of particles slamming into your hand every second. At the heliopause, the particles are so sparse you could fly a sheet of aluminum through and barely trade a whisper of energy. So yes, 50,000 Kelvin, but not a stove, not a flame. To get why, separate two ideas. One is kinetic temperature, average particle energy. The other is heat flux, how much energy moves per unit time. You can crank the first sky high and still starve the second if the density is low. Voyager didn't roast because there weren't enough electrons and ions to share their frenzy. Fewer billiard balls on the table means fewer collisions, even if each ball screams across the felt. So where does that kinetic frenzy come from? Start with charge exchange, the quiet saboteur at the boundary. Neutral hydrogen from the interstellar side drifts in, passes through magnetic curtains like they're not there, and swaps an electron with a hot solar wind ion. Suddenly, you have an energetic neutral atom, an ENA, carrying away momentum in a straight line, and a newborn cold ion sitting in the wind like a stone in a stream. The wind's fields grab that ion, spin it up, and bang, you've just moved ordered flow into random motion. That's heat. Pickup ions are the middlemen in this economy. They start as neutrals, get ionized by charge exchange or ultraviolet photons, and are picked up by the solar wind's magnetic field. They don't glide. They gyrate, forming ring distributions that feed turbulence. Turbulence is the cosmic blender. It takes big, organized motion and shreds it into smaller and smaller eddies until friction-like processes at tiny scales convert motion into thermal energy. No flame, just order dissolving into heat. Add shocks and things get spicier. Coronal mass ejections race outward and pile up in the heliosphere, steepening into shocks that press against the heliopause. When a shock crosses a gradient in density and magnetic field, it can reflect particles, accelerate them, and stir more turbulence. Some of that energy leaks across via reconnection, magnetic field lines from the sun and the galaxy snapping and rejoining, letting energy and particles trade neighborhoods. Each reconnection event is a small wire crossed in a vast circuit. Another way motion becomes hot. Now about that glow. The wall isn't a torch. It's neutral hydrogen energized enough to emit or to produce those ENAs that IBEX and Cassini imaged. ENAs are our messengers. Being neutral, they aren't herded by magnetic fields. They fly straight from the boundary to detectors near Earth, encoding where and how energy was deposited. IBEX's ribbon is essentially a bright return address stamped by regions where the draped interstellar magnetic field angles just right to reflect or generate ENAs efficiently. If the wall stores energy, ENAs tell us where the tabs go. Here's a whiteboard moment. A physicist I trust drew 3 arrows: turbulence, reconnection, shocks. Pick your poison, she said. All roads lead to heating. The fight in the literature is about proportions. Some models argue reconnection dominates, especially where the interstellar field presses hardest. Others stack the deck with turbulence fed by pickup ions. Still others show shocks doing the heavy lifting during solar max. The data say yes to all, but not equally, not everywhere, not always. That's why the ribbon brightens and dims with the cycle, why hotspots migrate, why Voyager hears a different tone after each storm. Language trips us too. Call it 50,000 K and people hear star, but stars are hot and dense. The heliopause is hot and thin. You need to camp there for a cosmic eternity to soak enough energy to raise a spacecraft's skin by a single degree. It's less furnace, more fever, a sign of stress, not a source that will burn you. That matters for headlines and for policy. Panic isn't useful, precision is. Meanwhile, the shape question lurks under the heating story. If the heliosphere is more croissant than comet, with twin lobes held by magnetic tension, then energy stacks unevenly. Lobes, folds, and polar cusps become natural places for reconnection and turbulence to pump up temperatures. ENA maps show anisotropies that fit this idea at some energies. At others, the old comet tail picture works. The truth may be nested, croissant-like near the flanks, tail-like far downstream. Heating will follow the scaffolding. And remember Voyager's metronome, the plasma wave tone. When solar storms push shocks outward, the tone shifts as those shocks ring the interstellar plasma. The pitch tells us electron density. The change in pitch over time tells us how quickly energy spreads and how thick the heated layers are. Match storm launch times at the sun with tone arrivals at Voyager, and you get a ruler, a way to measure the boundary's thickness and the speed at which heat percolates across layered shells. So the paradox resolves. No fire, yet heat. No burn, yet hot. The wall's temperature is the receipt for energy transfers at a contact boundary that never settles. It's the bruise we talked about, pressure meeting pressure, flow fighting field with charge exchange, pickup ions, turbulence and reconnection tallying the blows. And if it can glow in ENAs and sing in plasma tones, we should ask the obvious next question. Who drew the first sky map that proved the glow was real? The sky map that shouldn't exist. We asked who saw the glow first. The answer came from a satellite that never left Earth's gravity. IBEX didn't point a camera, it opened a mailbox. Energetic neutral atoms left the heliopause and flew straight in, untouched by magnetic fields, each one a stamped letter from the edge. After 6 months of collecting and turning, the first all-sky map came together, and there it was, a narrow, bright arc, a ribbon wrapping across the sky where no model put anything. Stakes landed fast. If that ribbon was a mirage, then our boundary physics was wishful thinking. If it was real, we were looking at a fence, a swath of space where energy preferred to go, where particles turned around, where the interstellar magnetic field draped in a way that picked out a single great circle. You don't get a structure like that by accident. It meant order. It meant the galaxy's field was steering the conversation. Action first. IBEX maps showed an excess of ENAs at specific energies, peaking where the line of sight made the interstellar magnetic field perpendicular. That geometry screamed resonance, conditions that reflected or generated ENAs efficiently. The ribbon shifted brightness with the solar cycle, not instantly but with delays that matched the time it took solar wind changes to propagate to the wall and for ENAs to make the return trip. The signal pulsed with the sun's heartbeat, yet it was stitched to the galaxy's field. 2 metronomes, 1 melody. Meanwhile, Cassini's Inca instrument, out by Saturn, saw a complementary glow at higher energies, painting a broader, fatter edge around the heliosphere. 2 very different detectors, 2 vantage points, same implication. The boundary wasn't a fuzzy smear. It had texture, ridges, folds, a highlighted curve. And far away, Voyager's in situ whispers. The cosmic ray tide, the magnetic firmness, the plasma wave tones, gave the maps a touch point. We could overlay sound on sight and the fit wasn't perfect, but it was close enough to change minds. Here's the human moment. At a briefing, someone said ribbon, and it sounded gentle, decorative. Then the plots hit the screen, a spear of brightness slicing the sphere of the sky. A communicator in the back muttered, "That's not a ribbon, that's a wall," and the word stuck. It wasn't precise, but it caught what people felt looking at the map, that sense of a boundary asserting itself. Impact ripple. The old picture of a neat comet-like bubble trailing a long tail didn't vanish, but it had to share the stage. The ribbon's alignment with the interstellar magnetic field suggested magnetic tension was doing more heavy lifting than gas pressure alone. Models that bent the heliosphere into 2 lobes, what would later be nicknamed the deflated croissant, started matching parts of the ENA pattern better than a single, smooth tail. At some energies and latitudes, the croissant fit. At others, a tail returned. The shape wasn't one thing, it depended on how and where you looked. But there was one problem, and it wouldn't go away. The ribbon moved. Over 11 years of IBEX, its brightness waxed and waned and its position nudged, tracking changes in the solar wind and the sun's field with a lag. If this was a fence, it wasn't nailed down. It breathed. Energy bands didn't play by a single rule either. Higher energy ENAs traced broader regions. Lower energy ones hugged the ribbon tighter. Any model that tried to lock the heliosphere into a single geometry collapsed under those shifts. While that was happening in data rooms, Voyager's team used the maps as context, not gospel. You don't steer by a mural, but the mural told you where the freeway bent and where traffic piled up. When Voyager heard a new plasma tone months after a strong solar eruption, IBEX brightened not long after in the same sectors, as if the wall had swallowed a shove, heated, and radiated a flood of neutrals back at us. The timing lined up well enough to make it a habit. Check the sun, check Voyager's ears, check IBEX's sky. Here, S where the croissant vs comet fight turned practical. If magnetic tension pinched the flanks into lobes, those lobes could host folds and cusps, places where field lines converged, where reconnection could pump heat and open temporary doors. The ribbon's persistence along one great circle could be the signature of that draping, a kind of magnetic highway where particles found the same angles over and over. Yet Cassini's wider glow hinted at a sheath that still swept tailward like a comet. The compromised picture got messy but useful. A croissant-shaped nose and flanks feeding a more traditional tail downstream. Complication piled on. The ribbon wasn't just moving, its spectral slope, how brightness changed with energy, refused to sit still. During solar maximum, some sectors flattened, consistent with stronger shocks and more pickup ion turbulence feeding ENA production. During minimum, the ribbon sharpened, as if quieter conditions let magnetic geometry dominate. No single heating mechanism could win everywhere. You had to juggle turbulence, reconnection, and shocks on a schedule the sun wrote and the galaxy enforced. Impact again. With IBEX and Inca, we had a weather map of the wall. Not perfect, not instant, but good enough to watch the fence flex. That mattered for everything from predicting cosmic ray backgrounds to picking trajectories for probes that might want to thread between hot zones. It also reframed Voyager's story. We weren't just listening to a boundary. We were seeing it choose paths for energy, lighting up where the invisible field told it to. Then came a cliffhanger worthy of headlines. Voyager crossed the line many thought would end the debate. The plasma wave tone leapt, the cosmic rays rose, the solar particles vanished. By the numbers, we were outside. But the maps kept shifting and the magnetic field direction near Voyager didn't pivot as cleanly as a modeler's sketch. The wall, it turned out, could be crossed and still reach back. The story wasn't over. We thought we were out until the wall sang back. Crossing day, not outside, just elsewhere. Crossing day didn't feel like a banner raising. It felt like a lab argument with a clock running out. The cosmic ray counters jumped and stayed high. The solar-borne particles that had ridden shotgun for decades fell to a whisper, and the plasma wave tone vaulted into a new register that matched electron densities tens of times higher than inside the heliosphere. By the numbers, we'd made contact with the very local interstellar medium. But the magnetic field's direction didn't swing the way the clean diagrams promised. It held steady, strong, but oddly familiar. Here's why that mattered. In the simplest picture, stepping across the heliopause should put you onto field lines aligned with the interstellar magnetic field. Different tilt, different twist. Instead, Voyager saw continuity. The field got firmer, but its orientation barely budged at first. Two teams looked at the same vector and said opposite things. One team said, continuity means we're still inside a solar-dominated sheath. The other said, strength and stability mean we're outside, but on draped lines that still mimic the inside. Words fail when boundaries fold. Meanwhile, the radiation told a clearer story. Galactic cosmic rays, the high-energy nomads from distant supernovae and more exotic engines, surged, especially at lower rigidities that the solar wind usually keeps at bay. Solar energetic particles, the sprinters from flares and coronal mass ejections, collapsed to near zero. That inversion is exactly what you expect when the sun's modulation no longer rules your neighborhood. If you were an astronaut in an unshielded capsule sitting where Voyager sat, your dose rate would have climbed, not catastrophically, but measurably. Another tick toward why this fence matters. The human moment came on a scratchy call that started 5 minutes late. One pi cleared his throat and said carefully, "We have unambiguous evidence of interstellar plasma density." Another answered, "An ambiguous evidence of magnetic topology." You could hear the smile that wasn't quite a smile. Reporters love clean lines. Scientists respect messy edges. Everyone knew both were true that day. So what actually happened at that border? Think laminated sheets, not a single skin. The heliopause behaves like layers of magnetic fabric pressed together, stitched by occasional reconnection. Voyager's path punched through one layer where particles mix but fields can still hold memory, then crept into another where densities reflect the outside but orientations keep a solar accent. In that picture, outside is a neighborhood, not a door. You can step onto the porch and still smell the kitchen. While that was happening far away, IBEX and Cassini kept us honest. IBEX's ribbon brightened in sectors that aligned with where the interstellar field draped most cleanly. Cassini's Inca maps showed a broader, higher-energy glow girdling the flanks. Neither map flipped on crossing day, because they never could. ENA images integrate over months and energies. But the slow evolution matched the idea that Voyager had entered regions feeding those maps. The taste matched the menu, even if the dining room lights were dim. Here's where the density spike from earlier paid off. That first high-pitched plasma tone gave us a number for electron density outside, a benchmark. After crossing day, subsequent tones climbed and fell around that number when solar shocks slammed the boundary. The cadence let us time how thick the layered sheath was and how quickly disturbances percolated. If the wall were a single sheet, echoes would be sharp and quick. Instead, echoes stretched, sometimes splitting into distinct hums, evidence for stacked shells with slightly different densities. The wall had texture we could hear. Then the magnetic puzzle added a twist. Over months, the field's direction edged toward the interstellar orientation. Not a snap, but a slow drift, like a boat sliding from a river's eddy into the main current. That slow-turning needle became the compromise everyone could live with. We were in the interstellar plasma by density and radiation, but still moving through a draped field transition where memory of the sun lingered. Outside, yes. Elsewhere, absolutely. Complications kept us from getting comfortable. The edge was porous. Voyager watched temporary inflows and outflows, brief returns of solar particles, small dips in cosmic rays, tied to sector boundaries and likely reconnection events. It was as if doors opened and closed along the laminated sheets, letting certain energies leak one way or the other. For mission planners thinking about crude timelines, that porosity mattered. A quiet month at the sun didn't guarantee a quiet month at the edge if a magnetic zipper pulled open. Meanwhile, something else was happening that nudged language. Early press called it leaving the solar system. Engineers flinched. The solar system, by gravity and comets and dust, reaches much farther. What Voyager left was the sun's supersonic wind. What it entered was interstellar plasma shaped by the sun's last reach and the galaxy's first grip. Get the words right and the physics follows. In the aftermath, a consensus formed like sediment. Crossing day wasn't a flag on a line. It was the first step into a braided borderland where densities, fields, and particles don't switch all at once. The headline outside was earned by the plasma wave hum and the radiation flip. The asterisk, just elsewhere, was earned by the magnetic continuity and the layered echoes that followed. Porous means one more thing, though, and it's the part that keeps flight surgeons awake: leaks. The leaks, cosmic rays find the cracks. Porous sounded poetic until the counters proved it. If the wall were perfect, galactic cosmic rays would rise to a flat new normal and stay there. They didn't. Voyager saw anisotropies, tiny imbalances in arrival directions, like a draft in a room with a hidden window. From one angle, flux ticked up, from another, it eased. Particles were finding preferential paths. The edge had seams. Stakes hit home fast. Cosmic rays aren't abstract. They flip bits in avionics, seed cataracts, and carve DNA. A leak at the heliopause isn't just a curiosity at 100 astronomical units. It's a long fuse that runs straight to a flight surgeon's spreadsheet in Houston and to a radiobiologist's notebook on a campus far away. A tight seam means fewer millisieverts. A zipper open an extra inch means more. Action first. Voyager's instruments mapped gradients, how intensity changed with position. Not much motion, but enough. As the spacecraft drifted outward, fluxes didn't just climb and level. They bobbed with a pattern that tracked magnetic sector structure. When the interstellar magnetic field folded against draped solar fields, the geometry made funnels, energy-dependent gates where some rigidity slipped through while others were steered aside. At lower energies, modulation still mattered. At higher energies, particles barely noticed the fields and walked in anyway. The wall wasn't a single filter. It was a stack of sieves with different mesh sizes. Meanwhile, the plasma wave metronome kept time in the background. After big solar eruptions, shocks reached the boundary and the tones rose, telling us electron density had swelled. Right after those rises, Voyager often recorded subtle changes in cosmic ray flux. The sequence hinted at a mechanism. Shocks pressed the laminated sheets together, reconnection flared, and temporary corridors opened. For days to weeks, certain energies found easier passage. Then the corridors pinched off, and the pattern retreated. Unknown to them across town, the IBEX team watched the ribbon flutter with the cycle. During brighter ENA periods, when the boundary was dumping energy into neutrals, Voyager's leaks sometimes looked different. Where the ribbon marked strong draping, anisotropes grew sharper, as if the same geometry that lit the map also shaped the portals. Not a one-to-one mirror, but a family resemblance you couldn't ignore. Here's the human moment. In a conference side room, a flight surgeon spread dose maps for a Mars flight across a table. She tapped one corner. If the wall opens like it did in year X, we need 10% more shielding margin on this trajectory. That's mass we don't have. On her notebook's inside cover were names, colleagues lost to cancer, penciled like reminders that numbers touch lives. She smiled, but the math didn't. Complications piled in with the sun's mood. During solar maximum, the inner heliosphere softens cosmic rays more, but the boundary gets rowdier. More shocks, more reconnection, more transient doors. During minimum, the inner suppression eases, so baseline galactic flux rises, but the wall may sit quieter, until a stray eruption finds a stressed fold and pries it open. North and south lobes didn't behave identically either. Asymmetry in the draped field meant one polar region could leak while the other held, a cosmic version of Earth's magnetospheric cusps that funnel particles toward the poles. Parallel action brought a scale model to mind. Earth's magnetosphere has dayside reconnection that opens field lines and cusp funnels where energetic particles pour into the upper atmosphere. Satellites skim those cusps and watch dose rates jump. The heliopause looked like that writ huge, layered curtains that, under the right stress, unzip to form narrow paths. The difference is distance and delay. At Earth, cusps pulse on minutes. At the heliopause, doors breathe on weeks to months, and our detectors hear them with travel time baked in. Impact hit with nuance. The wall filters, but not perfectly. It's energy selective and time variable. For astronauts beyond Mars, that means dose budgets you can't set and forget. You plan during solar max to cut galactic rays, but you brace for solar storms and boundary leaks that punch above their weight. During minimum, you accept higher cosmic background and hunt for quiet windows in a calmer wall. Either way, mission timelines start to respect a shield's seasons as much as a planet's alignments. Then something unexpected happened in the numbers. Voyager recorded small, coherent swings in cosmic ray flux aligned with sector boundaries traced by magnetic orientation changes. Even this far out, faint memory of the sun's sector structure seemed to modulate the leaks. It was as if the laminated sheet still carried a watermark of solar polarity, guiding which corridors formed and which closed. That detail mattered, because it meant prediction didn't have to be guesswork. It could ride on solar data we already track. But there was one problem. Our eyes are few. One spacecraft can't triangulate a corridor. ENA maps integrate too slowly to catch a 2-week door. Without more scouts, our modelers were stitching quilts from scraps. The plan that took shape was simple and hard. Launch an interstellar probe with fresh instruments, add inner heliosphere monitors, and watch the sun's eruptions from cradle to wall. Link the shock at the sun to the tone at the edge to the leak in the cosmic rays. Turn anecdotes into a forecast. In the aftermath, a new kind of weather report felt possible. Not whether it'll rain on Tuesday, but whether a seam at the heliopause would widen next spring, shifting dose rates by a few percent for a crew outbound. That's not fear-mongering, that's respect. Because if the wall can leak, it can, under the right outside pressure, fail more broadly. If it leaks, can it fail? Only if pressure changes from beyond. The Interstellar Weather Report. If leaks mean vulnerability, then what's outside the fence matters as much as what's inside. Call it interstellar weather. We're not sailing through a uniform fog. We're drifting through a neighborhood of clouds, filaments, and magnetic seams that change the pressure on our bubble. Push harder from outside, the bruise deepens and moves. Ease up, it relaxes. That's not theory, it's trajectory. Start with where we are. The sun is plowing through the very local interstellar medium at about 26 kilometers per second, threading a patchwork known as the local ribbon of cold clouds. These aren't storm clouds. They're reservoirs of mostly hydrogen, partly ionized, with temperatures of a few thousand Kelvin and densities that can jump by orders of magnitude from one pocket to the next. The local interstellar cloud, our present address, sits near boundaries of colder, denser neighbors. Edges in space aren't crisp. They're ragged, threaded with magnetic field lines that can stiffen them like rebar. Magnetic field direction is the first forecast variable. IBEX's ribbon geometry and starlight polarization tell us the interstellar field tilts relative to the ecliptic and drapes around the heliosphere. That draping sets where tension piles up and where folds form, those same folds that shaped leaks in the last act. If the field rotates as we cross a cloud boundary, the drape changes. New lobes stiffen, old cusps soften, and the wall's hotspots migrate. You don't need a collapse to feel that. A few nanotesla shift in direction changes where the fence creaks. Density is the second variable, and it's the blunt instrument. Raise the neutral hydrogen density outside and ram pressure on the heliopause climbs. Increase the ionized fraction, and magnetic pressure matters more too. Either way, the termination shock creeps sunward, the heliosphere thins, and the heliopause presses inward. Modelers run scenarios where a move into a denser cold cloud, think the local Lynx of cold cloud, shrinks the heliosphere to a fraction of its present size. In some runs, the stagnation point tucks inside Pluto's orbit. In the most extreme cases, the bow wave tightens and the sun's cocoon folds so far in that Earth grazes the edge. Here, where the past whispers warnings. We've found life 60 feet, an isotope forged in supernovae, buried in ocean crusts and Antarctic snow, dated to a few million years ago. That's a signature of nearby stellar events and altered space conditions. Recent studies go further. Simulating passages through cold, dense clouds suggests the heliosphere might have collapsed inward to sub-AU scales during epochs around 2 to 3 million years ago. If Earth stepped outside the shield, even briefly, cosmic ray flux would have spiked. Climate proxies hint at shifts. Atmospheric chemistry would have felt it. We can't claim causation cleanly, but the forensic dots line up enough to respect the possibility. I remember a model run that turned the room quiet. On the wall, a 3D heliosphere color-coded by pressure shrank as the external density slider nudged right. The termination shock slid from 90 AU to 40, then 20. The heliopause followed. Pluto's orbit, once buried in the sheath, lay naked. Someone exhaled. No one joked. The conclusion wasn't doom, it was scale. The fence moves. It has before. It will again. Complications keep humility in the mix. We don't see these clouds like we see weather fronts on Earth. We infer them. Ultraviolet absorption lines in starlight tell us column densities and ionization fractions along certain sightlines. Polarization maps sketch magnetic direction statistically. IBEX and soon IMAP trace neutral hydrogen via ENAs, but boundaries are patchy. Velocities vary within a single structure. What looks like a wall can be a tangle of filaments. Our forecasts carry error bars wide enough to park a starship in. There's another open question that tweaks the forecast. Do we have a bow shock or just a bow wave? If the sun's motion through the VLISM is fast enough relative to the local fast magnetosonic speed, you get a true shock upstream, a sharp, heating, compressive front that preconditions the gas before it meets the heliopause. If not, you get a gentler bow wave. That difference matters for where and how heat accumulates. A shock deposits energy upstream. A wave lets more pile onto the heliopause itself. Heating patterns, ENA brightness, even leak dynamics change with that upstream answer. Meanwhile, the sun keeps a hand on the thermostat. Solar maximum pumps more pressure into the heliosphere and thickens the cushion. Solar minimum lets the cushion sag. Layer that decade scale breathing over million-year drifts through cloud ensembles, and you get beats within beats. Sometimes a quiet sun meets a soft cloud and the wall rests. Sometimes a quiet sun meets a dense filament, and the heliosphere tightens like a belt. Mission planners don't get to pick the background song, but they can learn its rhythm. Parallel action back on Earth turns this into policy. A surge in galactic cosmic rays during a thinner shield means higher dose rates for aircrew on polar routes, more single-event upsets in satellites, and subtle nudges to atmospheric chemistry that modulate cloud microphysics. Not a switch, but a slider nudged a few percent in a system that integrates small changes over time. That's not clickbait. That's a line item in risk ledgers from airlines to power grids. So what do we do with a weather we can't see directly? Build better eyes. Keep ENA imagers running, IBEX now, IMAP soon, to track ribbon shifts and global brightness. Fly ultraviolet spectrographs to map interstellar hydrogen glow. Launch an interstellar probe with magnetometers, plasma analyzers, and a fresh plasma wave ear to sample the VLISM from multiple angles. Tie solar storm catalogs to boundary echoes and learn the time constants. And keep digging in ice and ocean for isotopic breadcrumbs that tell us how the fence moved in deep time. Because there's one more forecast nobody wants but everyone needs. If cloud pressure climbs, the wall can thin to the point where leaks stop being seasonal seams and start being sustained gaps. That's not inevitable soon, but it's not hypothetical either. Preparedness beats panic. And there's another hand on the thermostat, the solar cycle's hidden hand. And there's the hand we can actually watch, the sun's. Every 11 years or so, it flips its magnetic polarity, tangles and untangles its own field, and breathes pressure into the bubble that cushions us. That cycle isn't background noise. It's the hidden lever on the wall's thickness, its leaks, and even the way it sings. Start simple. During solar maximum, the sun's surface boils with active regions. Coronal mass ejections punch off like freight trains, the average solar wind pressure inches up, and the heliosphere swells. The heliosheath fattens, the termination shock can edge outward, and the heliopause feels a firmer push. During solar minimum, eruptions wane, the wind's pressure eases, and the sheath thins. Think of a lung filling and emptying, slow, deliberate, consequential. Why does that matter at the edge? Modulation. The sun's changing magnetic field threads the outflowing wind, building a spiraling scaffold that incoming cosmic rays must navigate. In solar max, that scaffold is knotted and strong, scattering more low to mid-energy galactic cosmic rays and keeping their intensities lower in the inner heliosphere. In solar min, the scaffold loosens, and those same energies find easier paths inward. That's why radiation dose rates for deep space missions anti-correlate with the cycle. Worst for galactic cosmic rays during quiet suns, tempered during rowdy ones. But that's the inner story. At the wall, cycle effects get stranger. All those shocks launched during maximum don't vanish. They stack and steepen as they plow through the heliosheath. When they slam into the heliopause, they press the laminated sheets together, pump energy into turbulence, and trigger magnetic reconnection. That's heating by appointment. The plasma wave hum that Voyager hears tends to spike after strong solar activity, tones rising as outside electron densities swell slightly and the interstellar plasma rings. The cadence lines up, eruption, transit, echo. Meanwhile, IBEX watches from near Earth and sees the wall's response in ENAs. Over 11 years of data, the mysterious ribbon brightened and faded with the solar cycle, but not instantly. There's a built-in delay that matches the travel time for solar wind changes to reach the boundary and for ENAs to fly back. During solar max, some sectors of the ribbon flatten in spectrum and fatten in brightness, consistent with more shock-driven heating and pick up ion turbulence pumping ENA production. During minimum, the ribbon sharpens and shifts subtly, as if magnetic geometry, draping angles, field strength, regains control. Here's where the croissant versus comet debate sneaks back in with teeth. The solar cycle doesn't puff the bubble evenly. The sun's magnetic equator is tilted relative to the interstellar field, and the cycle's polarity flips reshuffle how that tilt threads the wind. North and south lobes don't inflate symmetrically. One season, the northern lobe might stiffen. In another, the southern lobe carries more tension. Tail regions can twist, with one flank tightening while the opposite relaxes. Those asymmetries matter because they steer where reconnection prefers to light up and where leaks are likeliest to form. A mission planner once put it like this: we don't launch into a vacuum, we launch into a mood. During solar max, crews enjoy reduced galactic cosmic rays but must weather more frequent solar energetic particle events. You add storm shelters, watch the sun like a hawk, and accept that the wall may flash hot with more transient doors. During solar min, you plan around higher baseline galactic radiation, but you also count on a quieter heliopause, fewer shock-triggered zippers, unless a lone eruption arrives at a bad angle. Trajectories and timelines bend to a star's calendar as much as to planetary alignments. Now about those transient hot spots. Cycle-driven reconnection is a prime suspect. When solar polarity flips and the interplanetary field rotates, it rearranges how draped lines from the sun tangle with the interstellar field at the heliopause. Oppositely directed lines meet, reconnection sparks, energy jumps across. Localized regions heat up and produce more ENAs, brightening slices of the ribbon. As the cycle advances, those sparks migrate with the geometry, painting shifting arcs that IBEX and soon, IMAP can track like a slowly moving aurora at the solar system's skin. There's a detail the 30-second rule would beg us not to skip: time constants. From eruption to boundary, shocks take months to a year to arrive. From boundary to detector, ENAs take days to weeks depending on energy. From boundary to Voyager's antennas, the density, hum, travels at the local plasma's characteristic speeds, so the echo's timing encodes distance and structure. Tie those clocks together and you get a forecasting tool, a way to connect a flare on a Tuesday to a hotter, louder wall months later, and to a brief shift in cosmic ray leaks not long after. But there's one complication that keeps modelers busy. The solar cycle's imprint isn't sinusoidal and clean. It's lumpy. Maxima can be double-peaked. Minima can linger. High-speed streams from coronal holes persist into minimum and carve co-rotating interaction regions that behave like second-tier shocks, drumming the heliosheath in slower, steadier beats. Those streams can bias heating towards certain longitudes, skewing ENA brightness and tweaking leak patterns in ways a simple max hot, min cool framework can't capture. Human moment. I watched a team slide sticky notes across a wall calendar, launch windows, cruise phases, solar forecasts penciled with confidence that faded 2 years out. Someone laughed, not unkindly. We're scheduling a road trip with a driver who sometimes naps. They kept going, because even a fuzzy forecast beats flying blind. In the end, the sun's cycle is the hand that shapes the wall's seasons, thickening and thinning the sheath, stirring shocks into song, shifting the ribbon's glow, and tilting where seams might unzip. We don't control that hand, but we can read it. Which brings us back to the sound that made the edge real, the wall's siren that lets us hear the cycle play the boundary like an instrument. The sound of a boundary, plasma waves as a siren. We'd been watching the wall breathe. Now we needed to hear it. Voyager's plasma wave system isn't a microphone, but it does the next best thing. It senses tiny electric oscillations in the plasma and turns them into frequencies we can plot, and if you want, play. The trick is simple physics. In a plasma, electrons slosh at a frequency that depends on how many of them there are. More electrons, higher pitch. It's a density meter disguised as a song. Here's how the performance starts. A solar eruption lifts off, fast, hot, magnetic. It pushes a shock into the solar wind, which spends months crossing the heliosphere like a distant freight train. When that shock piles into the heliopause and nudges interstellar plasma, electrons there start to ring at their natural frequency. Voyager's antennas, long and spare, pick up the oscillation. In a control room years and billions of kilometers away, a trace on a screen climbs into a whistle. The stakes are real. Without that whistle, we're guessing about where outside begins. With it, we get numbers you can hang a mission on. The first clean tones after the big crossing map to electron densities tens of times higher than the heliosheath. Not a hand wave, a calibration. Once we had that yardstick, every later tone became a waypoint, each pitch shift a hint about how the boundaries layers were stacked and how they were changing. Action then. A major coronal mass ejection erupts. Weeks later, instruments near Earth chirp as the front sweeps by. Months after that, the Voyager team watches their frequency plots. The line rises, a few kilohertz higher than last season, then levels. They check the sun's event logs, the shock's estimated speed, the expected travel time. The math lands within a margin you can respect. You can almost feel the shove cross the gulf, sun to sheath to wall to very local interstellar medium. Then right on cue, IBEX brightens along the ribbon sectors that geometry says should absorb more energy. Sight, sound, and timing click. Meanwhile, something else is happening that turns tones into topology. The echoes don't always arrive as a single, clean rise. Sometimes they step. One pitch climbs, holds, then a second, slightly lower tone joins like harmony. That isn't art. That's structure. Two neighboring layers with different electron densities got bumped at different depths, or the same layer thickened unevenly across Voyager's line of sight. The wall's not a sheet. It's laminated like we argued earlier. The Siren lets us count the laminae. Here's the human moment. A tech sits with headphones, not because the data require it, but because sound helps brains notice patterns. The hiss wavers. A faint whistle grows. She points at the screen. There, she says, and half the room leans in. Somebody laughs at themselves for trusting ears on a space plasma problem. It doesn't matter. The tone is physics, and the ear is a pattern detector honed by evolution. Use what works. Impact lands fast. With repeated shocks and repeated tones, we measure thickness. If a shove takes, say, 11 months to get from the sun to the outer boundary, and the ringing sustains for weeks at one pitch before sliding to another, that slide encodes how quickly energy diffuses through the layers, how viscous, in a plasma sense, the borderland is. Faster diffusion, quicker, smoother transitions. Stickier media, slow, step modulations. Those aren't just adjectives. They're the bones of models that forecast how leaks behave and how heating localizes. But there was one problem. Quiet stretches, long bouts with no tones aren't silence, they're ambiguity. Did the boundary calm, or did the sun simply fail to send a strong enough shock to ring it? Without a driver, the bell doesn't chime. That's why tying tones to solar event catalogs matters. When a big eruption happens and no echo follows months later, you learn something else. Either the path softened the shock into mush, or the geometry steered energy into another lobe. A missing note can be as instructive as a bright one. Parallel action across the hall, modelers feed in the timing. They set shock launch dates, propagate through the inner heliosphere with co-rotating regions sculpting the flow, push into the heliosheath where pickup ions fatten the plasma, and finally smack the heliopause with varying angles against the interstellar field. They let reconnection flicker where anti-parallel lines kiss. Out pops a synthetic siren. If the simulated tones do climb where Voyager's did, the model's wrong. If they split when the data were smooth, the lamination is misspecified. The wall critiques the model in the only language that matters: results. Meanwhile, IBEX adds color. During cycles of brightening, especially at energies that track pickup ion-fueled ENAs, certain sectors show elongated hotspots that drift slowly with the solar cycle's geometry. When Voyager's tones around those epochs skew higher or linger longer, we get a triangulation of sorts, a region that both glows in neutrals and rings in electrons. Soon, IMAP will tighten the cadence, shrinking the ENA integration window so we can line up notes and lights more precisely. That's how you turn a frontier into a map. Here's a micro story. After a lull, a strong CME launches. Months pass. The frequency plot on a Tuesday shows a gentle rise. Wednesday, it's higher. Thursday, a second tone appears. Friday, cosmic ray counts at Voyager dip a hair, nothing dramatic, just enough to notice. The team marks the board, shove, ring, slight seal tightening. A week later, IBEX's sector brightens. None of it's loud, all of it fits. In the aftermath, we stop pretending the wall is mute. It sings when the sun plays it, and the key it sings in tells us the density, the layers, and the way energy moves along the draped field. Hearing it is one thing. Using that song to survive it, timing missions, bracing for leaks, predicting doses, that's the heart of the next act. Life under a furnace that doesn't burn. Hearing the wall sing is science. Living under it is personal. Earth's biosphere grew up in the lee of a star that blows a bubble, and inside that bubble the worst of the galaxy's charged shrapnel is thinned, bent, and delayed. You don't feel that on your skin at noon. You feel it in mutation rates averaged over eons, in electronics that fail less often, in the quiet fact that life got the time it needed. Start with the two culprits that matter for us. Solar energetic particles are the sprinters, bursts tied to flares and coronal mass ejections. Galactic cosmic rays are the marathoners, ultra-relativistic ions from distant engines that don't care about the sun unless the sun is organized enough to matter. The heliosphere handles them differently. It can blow aside many sprinters in the inner system and modulate the marathoners' numbers, but it never erases them. The wall, thick or thin, sets the baseline we live with. Here's the stakes line in human terms. For a Mars crew in transit, dose budgets are the life and death math behind every kilogram you launch. With the heliosphere breathing thick in solar maximum, galactic cosmic rays drop, which helps, but solar sprinters spike, which hurts. During minimum, sprinters calm down, but the galactic background climbs, chewing through your yearly allowance millisievert by millisievert. You don't get a free year, you get trade-offs. Action, then numbers without the spreadsheet glare. Take a typical unshielded deep space environment during a quiet sun. You're looking at several hundred millisieverts per year from galactic cosmic rays alone. Add a storm shelter and smart trajectory timing and you can shave that. Tuck behind Mars for parts of a transfer, and its body helps. Fly during a stronger solar wind epoch, and inner modulation trims a few more percent. But if the heliopause thins or leaks flare, your tidy margins wobble. Meanwhile, planets respond in their own ways. Earth wears a magnetosphere and an atmosphere that tag-team the incoming flux. The magnetosphere diverts many charged particles poleward. The atmosphere breaks the rest into showers that mostly die long before the ground. What reaches airplanes on polar routes are secondaries, neutrons and muons, that tick dosimeters and flip bits. Space weather offices quietly adjust route advisories based on indices that trace the sun's moods and, indirectly, the state of our bubble. It's routine only because the routines are good. Mars plays a different game. No global magnetic field. A thin atmosphere that turns primaries into cascades that slam the surface with more gusto. Rovers carry radiation monitors that tick like slow metronomes. Crewed missions will need mass, water tanks, polyethylene, fuel, placed where people sleep and work, because you can't count on the heliosphere to be kind the whole trip. In that sense, the wall's variability becomes a schedule constraint. You don't just wait for launch windows set by orbits. You wait for seasons in space weather. Here's the human moment. A radiobiologist flips through a notebook that doubles as a memorial. Names line the inside cover, mentors, colleagues, family, some lost young. We shave millisieverts because they add up, she says. We argue about quality factors because tissue does. She's not dramatic. She's precise. Her models fold in spectra that depend on whether the heliosphere is puffed or pinched, whether solar polarity steers more particles into the ecliptic or out. Her pencil taps slow down when the talk turns to long missions during a quiet sun and a leaky wall. Parallel action in paleoclimate brings a longer view. Cosmic rays seed ionization in the upper atmosphere, which can tweak the chemistry that shapes aerosols, which can nudge cloud microphysics. It's subtle, a percent here, a percent there, but the climate system integrates small nudges. Proxy records show cosmic ray variability that tracks the solar cycle and longer drifts. You won't hang an ice age on a single slider, but the heliosphere's modulation belongs in the set that sets the stage. Complication keeps us honest. Shielding is never just more mass. It's what kind of mass where you put it and what secondaries it makes when a high-energy ion slams into it. Aluminum stops some particles but breeds showers at certain energies. Hydrogen-rich materials slow protons cleanly but take space and weight. Active concepts, mini-magnetospheres, electromagnetic fields, promise local cocoons around ships, not global fixes at the heliopause. We can bend the rain around our umbrella. We can't reshape the storm front. Meanwhile, the wall's hot. That doesn't burn threads back into mission design. A 50,000 K boundary won't heat a hull, but it signals where energy is being dumped, where ENAs will brighten, where reconnection is prone to flicker. Those same places are where leaks like to breathe. If you're planning a probe to skim the flanks, you thread between hotspots the way a pilot threads between cells on radar. For crewed vehicles, you accept you'll never get that close and use the map anyway, because what the wall does today changes the background you'll fly through next year. Impact lands in 3 buckets. On Earth, the wall's thickness and the sun's mood set airline radiation advisories and satellite error budgets. In deep space, they set crew exposure and hardware reliability. Over geologic time, they set a quiet rhythm that life has already danced to: faster here, slower there, never still. None of it is cinematic. All of it is consequential. So yes, we live under a furnace that doesn't burn. We tune missions to its breath. We count on its filter, but we don't trust it blindly. Which leaves a sharp, tempting question hanging in the room. If this shield protects us, can we, carefully, locally, shape it? Tuning the shield, can we influence the edge? The question nags. If the wall breathes with the sun, can we nudge that breath? The honest answer starts small. We can shape fields locally. We can't grab the heliopause and tug, but local can matter when a human body is the payload and a spacecraft is the habitat. Action first. Picture a coil the size of a pizza pan in a vacuum chamber. A student dials current. The coil hums, the magnetometer needle twitches, and a whisper of plasma curves around a palm-sized mini-magnetosphere. It's a toy, sure, but it proves a point. Charged particles follow fields. Inflate those fields around a ship and you can bend some of the storm around you. It's not sci-fi. Plasma physicists have mapped the standoff distance where the pressure of an artificial field meets the ram pressure of a solar wind proxy. Get the pressure balance right. Magnetic pressure scales like B squared, and you carve out a pocket. Here's the catch that turns a demo into engineering. Space isn't a uniform stream of gentle protons. It's a spray of energies from tens of keV to tens of GeV. Your coil can deflect the slow ones. The fast ones laugh and plow through. To harden that pocket, you add plasma. Inject a puff of gas, let it ionize, and your magnetic field traps it. Now you've built a miniature magnetosphere with its own ring current. The plasma boosts the effective field, thickens the barrier, and lengthens the particle gyroradii you can influence. It's a feedback system. Field shapes plasma, plasma strengthens field. Get this, the trade-off isn't just power, it's housekeeping. Trapped particles don't vanish, they circulate. You've built your own radiation belt. Park crew modules where those belts are thinnest and put tanks where they're thickest, or your cure becomes its own disease. Radiation engineers sketch donut-shaped, no-go zones around habitat rings and place water, food, and waste as dynamic shielding. Active systems become architecture, not gadgets. Meanwhile, magnetic sails enter the conversation. Flip the idea around. Instead of shielding, use fields to push. A magnetic sail, a loop or set of loops projecting a field, lets the solar wind or the interstellar plasma push on your artificial magnetosphere and transfer momentum. In the heliosphere, it's thrust without propellant. In the very local interstellar medium, it's drag you can lean against to brake. The same physics that bends particles into a protective sheath can, in principle, move a ship. You won't tow the heliopause with it, but you might arrive at the wall with control over how you meet it. There's a human micro-story here. In a dim lab, a coil warms the air. A grad student watches Langmuir probe traces wiggle as she varies gas puffs into the chamber. The curve sharpens when the plasma fills in. She grins without theatrics, just the quiet smile of a measured improvement. On the whiteboard behind her, someone has scrawled Minimag, MaxiCare, and circled Charge Exchange 3 times. Because once you add neutrals and ions, you've also added the same process that heats the heliosheath, charge exchange that can create pickup ions and turbulence. Scale matters, but the principles rhyme. Now the boundary scale dreamers. Could we ever, even in theory, brighten or dim an entire sector of the heliopause by changing what we emit? The sun writes that script. Our transmitters, beamed power stations, or fusion exhausts are gnats at a hurricane. The energies involved in the heliosphere's pressure balance dwarf anything we can project. We can't tune the global wall. We can, at best, tune our local microclimates. Ships, stations, perhaps the immediate wake around a convoy. And yet local tuning scales into strategy. If you can build a portable pocket magnetosphere, you can ride thinner seasons of the solar cycle with less mass. If you can inflate it during solar energetic particle storms, you can flatten dose spikes. If you can reshape it to shepherd charged dust away, you buy reliability. Tie that active shield to a forecast that listens to Voyager-like tones and watches IBEX IMAP ENA maps, and you're not guessing. You're piloting in weather. But there's one problem that keeps ethicists in the room. Active systems change environments. Trapped particles leak somewhere. Artificial fields can couple to natural ones. Around Earth, we've learned the hard way that high-power radio and injections can seed artificial belts that linger. In deep space, a ship's mini-magnetosphere might focus flux downstream, a faint radiation shadow that another craft could stumble into. You don't need a treaty to fly a coil, but you do need norms, traffic rules for invisible wakes. Parallel action in the lab. Electron beams and plasma plumes test how fields reconnect when artificial and natural geometries meet. Reconnection is both friend and foe. It's how a mini-magnetosphere sheds stress. Magnetic lines snap and rejoin, shedding energy as heat and waves. It's also how a protective bubble can unzip if driven too hard. Engineers write control loops that watch for precursors, growing currents, rising wave power, and bleed power from coils before a runaway reconnection dumps your pocket in a burst. Shielding becomes control theory married to space weather. Impact, immediate and modest, looks like this. We can't smooth the galaxy's hand on the wall. We can build umbrellas that flex with the rain. We can move millisieverts from the column that kills to the column that ages. We can reduce single-event upsets enough to let fly-by-wire starships trust their own nervous systems. And we can practice in cislunar space, where Earth's magnetotail gives us a rehearsal room with real currents, real reconnection, and real surprises. Open loop by design. If we can't move the wall, we have to predict it. Tuning the shield doesn't end at the coil. It starts with scouts at the edge and eyes in the sky that tell us when the bruise deepens and where the seams unzip. Prediction demands one more leap. New scouts the next Voyagers. Prediction starts with presence. The wall sings, but our ears are old and few. Voyager's RTG warms less each year. Its memory sputters. Some instruments have gone quiet for good. If we lose that ear, we don't just lose romance. We lose the metronome that turns solar eruptions into boundary physics. We need new scouts, faster, sharper, coordinated. We need the next Voyagers. Action first. On a drawing board at APL, there's a spacecraft that doesn't tiptoe. It sprints. Call it Interstellar probe, a bus with a long-lived RTG, a high-gain antenna big enough to talk across a century, and a payload chosen by hard lessons. Not one plasma analyzer, several, tuned for the very local interstellar medium. A magnetometer on a boom that won't hear its own heartbeat. A plasma wave ear with more dynamic range than Voyager ever had. ENA imagers that see the wall in more colors, with tighter cadence, so we don't wait half a year for a map to coalesce. The mission profile is blunt. Get out fast. You don't spiral, you kick. Gravity assist at Jupiter at a burn your nerves can stand. Maybe you flirt with solar Oberth, dip deep into the sun's well behind a heat shield, fire a high-thrust stage and trade sweat for speed. The point is distance per year. 30 AU a decade is nice. 40 is better. You want to cross the termination shock with gas still left in the tank and a clock that can tick through multiple solar cycles. Meanwhile, something else is happening closer to home. IMAP, the Interstellar Mapping and Acceleration Probe, spins near the Sun-Earth line, gathering ENAs with better energy resolution and faster refresh than IBEX ever could. Pair an inner sentinel like IMAP with an outer runner like Interstellar Probe, and you get stereo. One eye watching the walls glow from within, one hand touching the wall from without. A solar eruption leaves the sun. Inner monitors time its birth. Months later, the outer scout hears the ring. Days to weeks after that, IMAP sees the ribbon brighten. Link those clocks, and the wall stops being a painting and becomes a live feed. Here's the human moment. An aging engineer pins a fresh patch, sleek, unfamiliar, next to his frayed Voyager emblem. He doesn't speak long. Same road, longer stride. Across from him, a younger systems lead sketches margin boxes around power, data rate, and thermal budget. She circles autonomy 3 times. Because communication at 200 AU isn't like pinging a Mars orbiter. Commands crawl at the speed of light, and light is slow on that scale. The next Voyagers have to think for themselves when a shock hits, and the instrument suite needs to change its plan. Complications come with the timeline. Funding cycles blink on human years. The wall moves on star years. You need a public that can care about a mission whose first headline might be a decade away and whose best science lands when kids now in grade school are running labs. You need power sources that won't die the way plutonium pipelines did. Advanced RTGs with higher conversion efficiency help. So do disciplined payloads that sip, not gulp. A mission that lasts half a century survives not by bravado, but by thrift. Action broadens. Don't fly one, fly a fleet of sorts. You won't get 3 flagships, but you can build a constellation by pairing one deep outrider with mid-distance Voyagers, smaller craft on solar electric arcs to the outer planets, each carrying lean packages, a magnetometer, a plasma probe, a dust counter. Add CubeSat-class hitchhikers released near Jupiter to sample off-ecliptic latitudes. One crosses a lobe, another skims a flank. They won't outlive the flagship. They don't have to. They fill in angles the big craft can't. Parallel action on Earth makes those scouts smarter. Radio arrays listen for interplanetary scintillation, the twinkling of radio sources through solar wind turbulence, to map streams that become tomorrow's co-rotating interaction regions. Solar telescopes feed CME catalogs with better speed estimates. Ground-based polarization surveys refine the interstellar magnetic field's tilt. Feed all of that into models tuned by Voyager's tones and IMAP's ENAs, and the next Voyagers don't wander. They sample on purpose, timed passes through predicted hotspots, parked integrations where draping should sing loudest. There's a micro-story in operations. A shock leaves the sun. Weeks later, DSN schedules stretch to catch a predicted echo. The outer scout shifts its plasma wave instrument to a higher gain mode, drops magnetometer sample rates to preserve storage, and cues an onboard algorithm to hunt for multi-tone splits. If it finds them, it flags a downlink priority. At the same time, IMAP increases dwell time on ribbon sectors most likely to flare. A week later, 2 teams trade notes. The echo's pitch rose exactly where the ENA brightness fattened. A modeler smiles without triumph. It's just one storm, but the chain worked. Impact looks like a weather service for a border we can't see. Not a daily forecast, cadence is too slow, but a seasonal outlook. The wall's northern lobe likely to run hot next year, leaks likeliest in this longitude band. Cosmic ray background nudged up by 2% in year N+1. That sounds small until you're closing mass budgets for habitat shielding or choosing avionics hardening for a Europa mission. The next Voyagers won't just collect postcards. They'll write advisories. But there's one problem we can't soft pedal: patience. You launch into a century, teams turn over, standards drift, file formats fossilize. The remedy is culture, open data by default, redundant archives, cross-trained operators, a cadence of public releases that keep attention alive. You tell the story as you go, not as an epilogue, so the mission doesn't have to be rediscovered every 10 years by a new crew. Payoff comes in coordination. A shove at the sun, a ring at the wall, a glow in ENAs, a leak in cosmic rays, measured from inside and out, across energies over years. Thread those beads and the wall stops being a rumor. It becomes a place we can forecast around. And right before we aim those forecasts at the far future, there's one unsettled argument we have to face head-on, because it sets the frame for every map we draw. Is the heliosphere a croissant? We've been mapping hotspots and listening for layered hums, and a shape keeps peeking through the noise. Not the tidy comet tail from grade school posters. Something pinched at the sides, lumpy at the poles, with tension lines that pull like elastic. Get this, the wall might not be a balloon, it might be a pastry. Here SY croissant even entered the room. IBEX's ribbon didn't trace a symmetric halo. It lit a great circle that hugged where the interstellar magnetic field drapes most strongly. Cassini's Inca added a thicker, higher energy glow that curved around the flanks. Put those together, and gas pressure alone can't explain the pattern. Magnetic tension has to matter. When you add the sun's wound-up field lines inside the heliosheath, they push back unevenly against the galaxy's field, pinching the flanks into two lobes and leaving a trough in between. That's the deflated croissant idea. Twin arcs held by magnetic rubber bands. Action, not metaphor. Modelers spun up full MHD runs with pickup ions, charge exchange, and a tilted interstellar field. In those runs, the heliosphere's nose didn't swell smoothly toward a single tail. It split. Two lobes arced backward, separated by a ribbon of lower pressure where field lines threaded tailward. At some energies, simulated ENA maps from that shape matched IBEX's brightness gradients better than a comet picture did. Regions where draping should be strongest became bright. Areas where tension relaxed dimmed. It wasn't perfect, but it was enough to put pastries on slides at serious conferences. Meanwhile, the comet team wasn't wrong. At higher energies and longer scales, Cassini's Inca saw a broader sheath that still fed downstream like a tail. And there's physics for that too. Pickup ions puff the heliosheath unevenly but don't erase momentum. Far enough back, the sun's outflow and the interstellar flow still stream into a downwind wake. The compromise came into focus. The near nose and flanks can be croissant-like, two-lobed and tension-held, while far downstream behaves comet-like. Scale and energy, pick your picture. Here's the human moment. In a packed session, a croissant proponent clicked to an ENA map with overlaid lobe contours. A hand shot up from the comet's side. At 50 kV, your fit collapses. The presenter nodded. At 50 kV, Inca owns the truth. The room chuckled, not unkindly. That's how arguments move without breaking. Stakes got practical fast. Shape isn't trivia. It tells you where the wall thickens or fails. If magnetic tension pinches the flanks into lobes, those flanks become natural sites for reconnection and turbulence, the same engines that heat and open doors. Polar regions where draped lines converge can act like heliopause cusps, guiding leaks. Equatorial bulges where pressure dominates might hold steadier but heat differently. A croissant means polar leaks and equatorial bulges. A comet means a more uniform nose and a cleaner downstream gate. Mission routes thread differently under each regime. Complication. Energy bands don't agree. IBEX-Low's lower energy ENAs emphasize places where pickup ion, fed turbulence and charge exchange are strongest, often aligning with the ribbon. IBEX-High's higher energy smear brightness wider. Cassini's Inca pushes higher still and sees the sheath like a backlit fog. Depending on which energy slice you test, you can make a croissant win or hand around to the comet. Toss in the solar cycle, polarity flips, variable wind pressure, and the whole structure tilts, breathes, and warps. One year the northern lobe stiffens, the next the southern one sings louder. And we haven't even folded in the sun's tilt relative to the interstellar field. That skew means asymmetry by default. The heliospheric current sheet, Our wavy magnetic equator threads the outflow on a slant. Where its polarity meets the interstellar field in opposition, reconnection prefers to spark, inflating a lobe with heat and opening short-lived portals. Where it aligns, tension locks down. Over the cycle, those alignments migrate, so hotspots on ENA maps and the likelihood of leaks drift with them. That drift is a fingerprint of the shape underneath. Parallel action back at Voyager's line of sight. The layered plasma wave tones we heard, single hums that sometimes split, fit a lobe framework. If the spacecraft's path skirts a lobe's edge, a shock can ring two neighboring densities, a higher one in a compressed arc, a lower one in an adjacent trough. The ear hears harmony, the map sees a bright and dim pair. When a later shock arrives at a new geometry, the pair flips. That's not proof by itself, but it's a pattern that keeps showing up. Impact lands in policy space. If croissant-like lobes focus stress and leaks near the poles, crude trajectories that climb off the ecliptic might trade shorter travel for rougher radiation weather. Conversely, equatorial skims could enjoy thicker, steadier cushioning until a polarity phase lines up reconnection there. Probe planners start drawing corridors around predicted hot arcs, not just planets. Shielding budgets shift by a couple of percent because a lobe is likely to run hot 2 years from now. Those are small numbers until you're shaving kilograms that keep people alive. But there's one problem we can't wish away. Ambiguity persists. ENA inversions depend on assumptions about source distributions. Pickup ion physics at the sheath is messy. Voyager is a point sample along a single cut. IMAP will help with better cadence and energy coverage. A dedicated interstellar probe, offset from Voyager's path and instrumented to taste the VLISM cleanly, will help more. Until then, both pictures live, and maybe that's the point. Multiple shapes can coexist at different scales. The heliosphere is not a statue. It's a tense, breathing structure that changes with cycle and cloud. So where does that leave us? With a map that's honest about its smudges and a shape that warns us risks aren't uniform. Policy shifts from averages to contours. Pilots plan for lobes. Engineers design for leaks that prefer certain latitudes. And the rest of us hold a final question in mind, the one that quietly sharpened as the croissant took form. If the wall can focus heat and leaks, what happens when the outside pressure really climbs? The threat we don't see coming. Pressure from beyond is the quiet threat. Drift into a denser cloud, like the local Lynx of cold cloud, and the fence tightens. Ram pressure rises, the termination shock retreats, the heliopause thins, leaks stop being seams and start being lanes. Forensics hint it's happened. 60 feet in ocean crust, models collapsing the heliosphere to near-Earth scales. Fewer buffers, higher galactic dose, satellites glitchier, chemistry nudged. Warning times short, cloud edges are ragged and magnetized. IBEX IMAP watch the ribbon shift, plasma tones mark thickening. Preparedness wins. Monitor model time missions, harden hardware. The bruise can deepen fast. That wall is our bruise against the galaxy, protective, temperamental, and negotiable under pressure. If you want the next move, how the great attractors pull sets our broader road, watch The Companion now. Subscribe for deep dives into hidden structures that decide launch windows, dose budgets, and where we aim the next Voyagers. Comment with the edge mystery you put a probe through first.